Okay, so we were discussing negative feedback, and we are trying to connect your existing knowledge of negative feedback with amplifier design that we want to make, right? So again, so this is the block diagram that you are familiar with. And we know that V0 is G by 1 plus GH times Vi. And if G tends to infinity, then okay, so even if I put, before I put G tends to infinity, so let me express this in another form. So V0 over Vi is G by 1 plus GH. This is often referred to as, in this form, 1 over H GH by 1 plus GH. So the reason this form is often preferred over the former one for loops which fall in this single loop unidirectional topology is because ultimately what are we making this loop for? What do we want? What do we want V naught to be? I can't hear you. So we are putting all these things because we need to do something, right? What was the necessity of this? Yeah, and that stable value should be, expected stable value is Vi by H, right? That doesn't seem to be clear, because if that is not clear, the whole purpose of going through this negative feedback will be nullified. I mean, you will not get the essence of it. So why do we need a negative feedback loop? We need a negative feedback loop because we want a stable output, right? Stable, what I mean is that, so we are essentially trying to make a perfect solution when all the components are imperfect, right? When I say perfect, I essentially mean that I want, let's say, V naught to be equal to 2 Vi. The factor of 2 has to be made using components which keep on varying. Okay, so that will keep on varying with voltage change, with temperature change, and whatever change that you can think of. So if you have to make a perfect solution, a stable solution using imperfect components, you cannot simply do it by having an input and then put an amplifier and of expected value 2 and output to be equal to 2 Vi. That's not going to happen. So we are trying to do it using negative feedback. And the way negative feedback works is you observe the output and see whether the output is whatever you want it or not. If it's not, then you change something so that the output goes in the direction that you want. But in order to do all these things, you need to first understand what you want, right? So what you want in this case? Yeah, but that is all, G is imperfect, right? We cannot make a good G. If we were able to make a good G, then we wouldn't have needed these loops. But what is accurate between G and H? When I say accurate, you mean things that don't change with temperature, voltage, or anything. H doesn't change, right? So yeah, so H doesn't change. So essentially, we are looking for an output which is expected output in a best case scenario should be Vi over H, right? So that is why we express this in this form. That is, this 1 over H is expected output and you will get this expected output under what condition? Yeah, G is very large, or in this case, if I express it in this form, it is assumed that H never goes to infinity. The expected output goes to 1 over H when GH tends to infinity. Again, we write it in form of GH because GH has another name. It's called the open loop transfer function or the loop gain, right? We will use loop gain in this course. So GH is called the loop gain. So this is L tends to infinity. L doesn't stand for length or inductor. It's loop gain. Okay. So this is one of the reasons V naught over Vi is often expressed in this form. So in general, we tend to write V naught over Vi as transfer function ideal, that is when loop gain should tend to infinity, times this L by 1 plus L. And often this is also changed slightly. This is written in this form, 1 by 1 plus 1 over L. Now you will understand why 1 over L is an important, I mean, writing it in this form makes more sense later on. But till for now, just take my word for it that if you express V naught over Vi in this format, it will be helpful. Okay. So again, this ideal transfer function will appear only when the loop gain goes to infinity. Okay. Or in this case, loop gain should be much greater than 1. Ideally infinity, but in reality, it should be much greater than 1. So again, negative feedback loop will work properly. This loop will work as per our expectation only when GH is much greater than 1. If GH is much less than 1, it's not going to work as per expectation. Okay. Okay. So now, if we replace now the other thing that we did in last couple of lectures was to replace this entire block diagram with a transistor, and we understood that this contraption is this is essentially a summer followed by a amplifier, right? And again, for the next time, G need not be accurate. All you need to do ensure is that G is large. So we know how to make an amplifier with a large gain as long as meets certain constraints. And we also know how to make an amplifier which senses the difference of two signals, right? Even common source amplifier senses the difference of two signals, but common source amplifier has an issue that it loads the input in one of its terminals, right? If you send something to the source terminal is going to load whatever it is driving. So then we came up with another topology, which was a differential amplifier. And then we say that we'll replace this entire this plus minus gain times G term with that topology. And that topology was this. Again, in the small signal regime, this is floating, this is not grounded. I call this one Vi1, I call this one Vi2. And let's say I call this R1, I call this R2. Then we see that if I observe this voltage was some Gm times Vi1 minus Vi2, and this voltage was negative of that. Right? So we did this analysis in the previous class. Then we saw that, I mean, the next step obviously is to now see how do I integrate this into the negative feedback loop. Okay, so again, this structure is whatever you have on the left. Okay, okay. So now if we wanted a amplifier of gain K, what did we do? We essentially replace this edge with a resistive divider. Okay, so the same thing we are going to do here. Okay, so now we have two outputs to choose from, right? So we can say this is V01, this is V02. So this V0, where I am planning to put this resistive divider, it can be put either at V01 or at V02. right? So how do I know which is the appropriate terminal? So let's, if we don't know, just put it in one of the terminals and then we'll see, right? So let's connect this to this terminal. So let me call this feedback VF. Okay. And let's say this is VI. So now two things need to be done. So we have an input, which I have not shown here explicitly. We have an input. And this summer over here has two terminals, two input terminals. This block over here has two input terminals, right? So I have to connect this VI and this VF to either of those two terminals if I have to equate the two pictures. Okay, so in the absence of any more information, I can simply say that I'll just let me go ahead and connect this to this, this to this. Okay, so the stuff that we have to figure out now is, having connected this in the way that we have shown here, is the sense of the connection correct? When I say sense, I mean that do I know this is in positive feedback or do I know it is in negative feedback? So how will I establish whether the loop, now we have a loop because output gets connected to some part of the input and feedback. So whether the loop is in positive feedback or in negative feedback. So what sort of experiment do I need to do? Yeah, you can break the loop and then apply a increment. You can break the loop anywhere. Okay, but when I say anywhere, I mean it should be anywhere inside the loop you have to break. You cannot break something which is not a part of the loop. Okay, so where is the loop here? The loop here is this, right? And also another important thing, you have to break the loop. It is instructive to break the loop in the direction of the signal flow. Okay, so again, what I mean by that is whenever when I'm using this type of block diagram, there are certain inherent assumptions we are making. One inherent assumption that we are making is G and H are independent of each other. When I say independent, I mean the application of G does not change H, application of H does not change G, which means we are assuming that G and H are voltage controlled voltage sources, right? They don't load each other. That is one important assumption. The other important assumption is, in this block diagrammatic format, is that signal, this loop is unidirectional. By unidirectional, what I mean is when I say and put G and put an arrow like this, what I essentially mean is that if I apply an input V1, the output will be G times V1. It does not mean that if I apply an input here of value V1, this will become V1 by G. It does not mean this. The signal only flows from left to right, not from right to left. So it's a unidirectional element. And hence, this is also a unidirectional loop. The signal does not flow backwards. In a block diagram, it is easy to make, but in reality, none of the elements that you know are unidirectional. For example, a resistance signal can flow either direction, right? The capacitance signals can flow either direction. But fortunately, till now, we have seen in a transistor, the signal can, if I assume one of the terminals to be the gate, right? The signal flows only from gate. I mean, it is sensed at gate and then something happens at the drain and source, not the other way around. So to some extent, I can say that transistor is also a unidirectional device. You will see later on, it's not perfectly true, but I mean, for the purpose of this course, we can assume that a transistor is unilateral. So if the transistor is unilateral, then and this whole construct of this negative feedback loop, as we are studying it, is based on the fact that you can calculate loop gain by breaking the loop. Then you have to break the loop in some place where it is unidirectional. I mean, where it is one, which is unidirectional, and two, it is not loading. The effect, if you don't consider the effect of loading, then you will have a problem. Now, when I say effect of loading, what I essentially mean is, consider the circuit that we have drawn, that we are planning to analyze. So in this case, if I have to find an equivalence of the circuit on the left and the right, and I have to find out what is G as in the gain in that in the right hand side figure, what will be the gain of the amplifier that we see? What is the gain of this amplifier? So let me make it simpler. So let's say I have. So let's say I have a common source amplifier and I have this block diagram. So let's say this is not connected till as of now. So this is GM, this is RL or RD. So if I have to draw an equivalence of this topology with this topology, what is G? What do you think? What is G? Firstly, do you think these two topologies are similar? No or not? What I'm saying is that block diagrammic representation, can the circuit in the bottom be can be modeled into the on the block diagram on the top? Yes, right? So if I can model, then obviously I can break up this circuit into G and H parts, right? So let's do the easier one. What is H? If I assume that this is connected. So what is H? And this is V0, this is V0. One by K, right? H is what fraction of the output is fed back, right? So this is V0, this is H times V0. So H times V0 is fed back, right? So if I draw the equivalence, the stuff that is fed back is V0 over K, right? So H is 1 over K, okay? But what is G? GMRD, right? GMRD. Seems like G is equal to GMRD, right? So GMRD. Okay, good question. So when I say gain, I essentially mean, when I say, yeah, in fact, I mean, the way I have sketched, it should be minus GMRD because the gain is between here and here, right? But if I have to draw an equivalence and I'm essentially looking for these two terminals, right? But if you see the way it has been sketched, VI has been applied to the positive terminal here and VI will be applied to the negative terminal here. Right? So that's why. But yeah, let's say I limit myself to the magnitude part of it. Let's say I limit myself to the magnitude part of it, then mod of gain becomes GMRD. Okay. So now you see that now when I connect these two, do you think the gain between this terminal and this terminal will be GMRD or it will change? Let's assume the loop is broken, because if the loop is not broken, you'll not be able to find gain anyhow. Does the gain stay GMRD or it changes? What is the load that the common source amplifier is seeing now? Okay, so this question is right, exactly, right. So that's what I was trying to point at. So what I essentially meant is that when you are trying to make this loop, what are you essentially saying? You say that I will take an amplifier of certain gain G, and I will have a feedback factor H. I'll put them together. So when you are thinking independently, independently of G and H, then you are thinking that I'll put a common source amplifier. I know a common source amplifier has a structure like this. In isolation, that common source amplifier gives a gain of Gm times Rd. Now I put it back in the loop, combining it with H. So now, does this common source amplifier between its terminals give you a gain of GMRD? It does not, because this application of this H has changed the G, right? So H is loading G. So this is an example as to why the block diagram representation is not so easy. I mean, when it's not always straightforward to recast an actual circuit into the GH form, because it's not always explicit what is G. And sometimes it is not even explicit what is H. And they keep on interfering with each other. But it is not so difficult to find out what is GH. G times H, you can find out by simply breaking the loop, applying an input, and see whatever is returning. Okay. So that statement itself takes certain things into assumption. But in this course, we'll keep it simple. We'll just say that we'll break the loop in a place where there is no loading effect, right? So for example, in this case, I can break the loop here and apply an input here and observe here. But that will not be correct, because breaking the loop at the location that I have shown is essentially removing the effect of loading, right? But if I mean, there are ways of getting rid of this, but not something that we can cover in this course. So what we'll look for is a place to break the loop where there is minimum impact of loading or no impact of loading. And the place in this loop, there are two places where there is no impact of loading. One is here, because I'm not drawing any current, right? And another is here, again, because I'm not drawing any current. If you're not drawing any current, there is no effect of loading. I can as well break the loops, right? So now when we are doing this loop analysis using circuits, we have to look for a place where we can break the loop so that there is no loading, and apply an input in the direction of the signal flow. Again, direction of signal flow is important, because if I break the loop here, let's say I break the loop here, and I say that I will apply a test input here, and I'll observe whatever comes back here. That's not going to work, because signal cannot flow in this direction. Okay, so two important things. One, you have to break the loop in such a way that the loading effect does not come into picture if possible. And two, you have to apply a test input in the direction of the signal flow. Okay, fine. So we'll do that for this circuit. So we identify a loop, and the loop is this. That is also the direction of the signal flow, right? Because it is the direction of the signal flow in the loop, because the other direction it cannot go, because the drain voltage cannot influence the gate voltage, right? It's the other way around. Now the next thing is to find out, or rather the most important thing is to find out whether the sense of the loop is correct or not, whether it is indeed in negative feedback or it is in positive feedback. So let's break the loop somewhere. So if I break the loop here, and I apply just an increment. I don't need the value or anything. Just let's assume that the voltage increased. If the voltage increased at that point, what's going to happen to V0? increase or decrease? I mean, going up or going down? If I increase this voltage, what's going to happen to this current? It will increase. It will go up. That current will increase. Right? So I'm increasing the gate voltage. So the current in the direction that is shown will increase, which means V0 will go down. Right? It will decrease. If V0 decreases, VF, what happens to VF? Decreases, and these two are essentially connected, right, in the loop, which means any disturbance that I had enforced gets suppressed, right? So the sense of the loop is correct. The loop is trying to hold on to whatever it had, okay, and it's trying to mitigate the change. Similarly, you can think of it in this certain way that, let's say, the value of GM changed, right? If the value of GM changed, you can argue in a similar way that the loop will try, if the value of GM changes, V0 will tend to change, right? But because it is in a loop, the loop will try to enforce the old value of V0 because there is an action of correction, okay? Okay, so now, so by the way, had this VF been connected to this node, had this VF been connected to this node and not VI, we can go through the loop thing again, and you will see that it has a reinforcement effect. This is in a positive feedback, right? You can do it yourself and satisfy yourself. Okay, so this is as far as the sense of the loop is concerned. So this is all good. The other thing, now the second thing is finding out the gain of the loop, like loop gain, or GH or L. So one can, I mean, we can do the similar thing, right? So we break the loop. Let's say this is the place to break the loop because, again, no loading. So I will break the loop here. I'll apply a test voltage V test, and I'll observe V return. And what should I do with VI when I am applying a test voltage to find out the loop gain? Again, you can draw the analogy with respect to this case. So I am breaking the loop here, applying a V test, and trying to figure out what is V return. And my loop gain by definition is V return over V test, negative of that. So L is minus V return over V test. But while doing this experiment, what should I do to VI? So under what condition this return voltage will be equal to V test times L, negative of that? When I say condition, I mean that what should I? It should be 0, right? If it's not 0, it will have a linear combination of V test and VI. It will not, you will not get loop gain. In order to get loop gain, you have to short VI. Okay. So same thing, we do it here. We short VI. So let me sketch the circuit again. So this is incrementally shorted. I assume these two GMs are identical and these two Rs to be identical also. So we are breaking the loop here, applying V test, finding out this voltage, which is V return. So now I can do this for this total circuit, or I can use a simplification. And the simplification is I can use the Norton's equivalent of this diagram that we have derived in the previous class, right? So dealing with, it is much easier to deal with one current source and one resistance rather than two MOSFETs and two resistances, right? So I will simply replace the Norton's equivalent of this, and the Norton's equivalent of that was this was GM times V1 VI1 minus VI2, and this was some ROC, where GM was GM1, GM2 by GM1 plus GM2, which in our case is GM over 2, because both the GMs are identical. And ROC was twice R02 in parallel with RD. So you can look at your notes to verify this. Okay. Okay, fine. So what I'll do, I'll just simply replace this entire contraption with the Norton's equivalent. Okay. So I can do one, but again, the way I have sketched this, it seems like this is an independent current source, right? But this is not an independent current source. It depends on VI1 and VI2. It's essentially a dependent current source. Okay. So this is a dependent current source, and the dependency is based on two voltage terminals, VI1 and VI2. Again, the critical distinction with respect to common source amplifier, the current in both the terminals is 0, right? Otherwise, I could have as well used a common source amplifier. Okay, so there is a symbol which is widely used to represent this structure, and that symbol is that of similar to an amplifier. Let's say this is I out, and we call this GM. This is plus, this is minus. So this is called a transconductor. Okay, this structure is called a transconductor. The name might seem quite handful, but it should be obvious. The relationship between the output and the input and the output is that of what we are essentially saying is that the I out is proportional to some voltage, right? So the unit is that of conductance, right? So hence this conductor, and trans because the I out is not dependent on the voltages across it. It's dependent on voltages somewhere else. So they have a transfer of conductance, transfer of information from some other ports to some other ports. So this is a transconductor. And the value of that proportionality constant, we call it as GM or transconductance, which is in our case is GM1, GM2 by GM1 plus GM2, which is GM over 2. Okay. So again, you will see that it is easier to deal with things if we can abstract them into small boxes, right? So we are trying to box out that DFAM, right? We don't want to deal with 2 transistors, 2 resistors. I want to box the DFAM out into a smaller, into a manageable format. So essentially now the DFAM, our DFAM equivalent becomes this VI1, VI2, but the DFAM doesn't have an infinite output impedance, right? So I have this ROC, so that ROC comes here. So this becomes the DFAM. Okay. How do I get the values of GM and ROC? Those values I get by independently calculating the parameters from the schematic of a DFAM, right? So I analyze the DFAM, find out its Norton equivalent one-time effort, and then those expressions I'm going to club and put inside this small box. Okay. So the next thing to do is to put this box back into negative feedback loop, because now it looks like we have a manageable diagram which we can analyze and get some insight. So again, this becomes this is V0. This is supposed to be connected to the output. This is VF. So now tell me, this VF will go to the plus terminal or the minus terminal of the DFAM? in order to ensure that the loop is in negative feedback. Minus, right? Because again, if you're not sure, you assume that you have applied a disturbance anywhere in the loop, not necessarily here. So from the definition of this GM, of this transconductance, if I increase that voltage, the current is going to get sucked in, right? So essentially current is going to get reduced. Again, if you're not sure, go back to this definition. If VI1 increases, this current is going to increase. If VI2 increases, this current is going to decrease. Decreasing current means you are pushing current in the other direction, right? Or pulling current in. So if the negative terminal voltage increases, this current is going to get pulled in. So this voltage is going to get reduced. So this voltage is going to get reduced. So essentially you are negating the disturbance. Okay. Okay. So this becomes the loop. So what is the loop gain? How do I figure out what is the loop gain? So couple of things to do. Again, the same algorithm. One is obviously you have to short the input. Without shorting, you will not get loop gain. So I short the input incrementally, all in the incremental domain. Then I break the loop. I would like to break the loop in a place where there is no effect of loading, right? So can I break the loop here? So essentially, I want to break the loop, apply a test voltage. And all I have to ensure is that there is no loading. When I say no loading, what I mean is, if I apply a test voltage here, okay, even before that, let's say I break the loop here and I apply a test voltage here. And I will say that I will find out what is V return, where V naught is V return. This is V return. Let's say V test. Is this correct? No, why not? Yeah, so it's not in the direction of the current of the signal flow, right? So you will not get whatever you are supposed to get. So this is not appropriate. So again, so I'll apply a V test here and observe this voltage and we call this V return. Okay. So when I do this, do you think this is appropriate? It is in the direction of the signal flow, but do you think there is a loading effect? There is a loading effect because how do you know? If you are drawing current from the signal source, then you are essentially, you know that there is a loading effect because that current in the presence of, in the total loop would have been provided by this block, right? But now because you have broken the loop, that block is not able to provide that current, right? So essentially you are hampering the operation of the loop by breaking it at an inappropriate place. Now again, just for the sake of completeness, this is not necessarily a problem if you can handle the loading. There are ways of handling this loading, but again, out of the purview of this course, we will not go there. So we'll try to find out a place where I can break the loop, where there is no loading. So this is not that place. So let me remove stuff from here. So the only place there is no loading is this, right? Because I know that this negative terminal is a gate of another MOSFET. So I've just clubbed it into this box. This negative terminal is a gate of another MOSFET. So I can break it here, apply a test voltage, and I'll observe this V return. Okay. So now what will be V return in terms of V test? So if I apply V test here, and so now let's go around the loop and try to figure out what this will be. So if the V test has been applied in the way I have shown, what will be this current? So let's say I put the direction in the way that was originally intended to be. What will be this current? GM times V test, but plus or minus? Minus, right? So this will be GM times V test, negative. So what will be this voltage, V naught? And this should be simple, right? Where is this current going into? ROC and KR in parallel, right? So what will be that voltage? Minus GM times Vtest is the current times ROC parallel here. Okay. So what will be V return? That divided by K, right? So V return will be minus GM Vtest ROC parallel KR times 1 over K. So negative of V return over V test, which is the loop gain, is GM over K times ROC parallel KR. Okay. So now, I mean, you see that we have, we went from block diagram to a fully transistor level equivalent back to a block diagram. But this entire hopping that we are doing is just to make sure that our analysis is not only simpler, but it also gives us some insight about the design. Okay. So what insight is it giving us? We want L to be what? Much higher, much lower than 1. What? Much higher than 1, right? So now we see that our loop gain expression is this. So we want this expression to be much greater than 1. So now the value of this should be much greater than 1. So naturally, you see, there are two things to be done here. One is you either ensure that the GM over K you cannot change because that is what you want. So you want the GM to be as high as possible, or also you want this thing of parallel combination of ROC and KR to be as high as possible. Okay. So now one thing that you can do, one obvious thing that you can do is to say that I will choose the values of R in such a way that it does not load ROC or it does not load the GM. So that all I am bothered about is the ratio, right? Is the ratio of R and K minus 1R. I can choose an R to be very large value. That I can do. There is no harm in doing that. At least from whatever we have done till now, there is no harm in increasing the value of R. So if we choose a value, so choose KR such that it does not load the GM or does not load the transconductor. Now, when I say it does not load the transconductor, what I essentially mean that it does not load this contraption, not the GM only, because the GM will GM will always provide the current. Okay. So when I say this, what I essentially mean is that you can then say, I will design this entire stuff in such a way that KR is much greater than ROC. Right? So if KR is much greater than ROC, then what is the loop gain? Then your loop gain becomes GM times ROC over K. Right? So essentially, the loop gain becomes the gain of the defam divided by K. Okay. So let's say you want this structure to work properly and you are targeting a loop gain of 10 and you want K to be, let's say, 5, right? So then you have to target a loop gain, which is, when you say that we want, oh, okay, let me rephrase. So let's say if we want L to be greater than 10, say, then GM times ROC, that is the gain of that defam, should be greater than K times 10. 10K. Question? Yes. Perfect. Yes, you would have gone on, but
I couldn't go with that.
okay. So his question is, if we had simply removed RD, and in this case, anyway, this K minus 1 R and R is loading the transconductor, then why put the RD? Simply put this K minus, get rid of RD, open circuit RD, which in fact will work. But why do we need the RD? So the background is you need something to bias, right? When I put the biases together, I haven't put the bias together as of now. But when you have a common source amplifier, you need something connected to the VDD to bias the drain, right? So that's why we needed that RD. But it's not necessary that you have to always have an RD. For example, you can put a current source there, right? Instead of an RD, you can put a current source, and we have seen multiple architectures how to use a current source for bias. So if I put a current source there in the incremental model, RD will become open circuit, and it is exactly what you are suggesting is going to happen. Then the loop gain will become GM times KR. Right? That is, in fact, the next part. Next class, you will see that we'll try to do that exactly. Okay, so ultimately we have to, I mean, even though we are only dealing with small signal right now, we understand that there has to be a bias in order to generate the appropriate GM. Right? If you don't have a bias VDD, you will not have any DC current or quiescent current. If you don't have any quiescent current, you will not have the requisite value of GM.
But we can get the value by changing the R itself. But any given value of GM, we should alter R than the final output.
Agree, but how are you going to push? How are you going now? Think in terms of where are you going to add the voltage source? Not the voltage source, sorry, VDD. So let's say I want to establish a current I naught into that transistor. Now I'm talking about bias currents, right? So how are you going to ensure that the bias is provided while keeping the transistor in saturation? There are many ways. Can you think of one?
To keep the transistor in saturation.
Yes. Right, we have to, right? Otherwise, I mean, even though I am only dealing with small signal, the inherent assumption is that bias has to be provided, right? So I laid with this architecture because I know how to provide the bias for a common source amplifier, and the common source amplifier bias is generally provided by putting a VDD on top, right? But it's not necessary that this is the only architecture. Whatever you are suggesting can also be done by simply replacing the RD with a current source. Right, I can put a current source on top. The current source is supposed to put the current in, and let's assume that feedback and everything is working. So BGS will become appropriately developed, and all those things will happen. Now, when I break the loop and do this analysis, since I have a current source, I can simply remove the current source, right? So then, whatever you are suggesting is going to happen. The loop gain will become GM times this KR, because RD will go out of the loop, right? So that is something we'll see in the next class. Okay, so before we end today, what you see is that for a negative feedback loop to work properly, you need gain, right? You need loop gain, and the loop gain is essentially being provided by the differential amplifier. Now, there is another name that is used in the literature for this differential amplifier. It is often called the error amplifier. Okay, it's because what is the essence? What you are trying to do in a negative feedback loop? You are sensing the error and taking a corrective action. And in this case, you are also in the process of taking the corrective action, you are also amplifying the error, right? So you are essentially finding out what is this error voltage. So this is V error, right? So in our case, what is the error voltage? Error voltage is the feedback VI minus the feedback voltage, right? So error voltage is VI minus VF. So this voltage is essentially the difference of this voltage is the error voltage, right? So this amplifier is often also called an error amplifier, right? Essentially all are the same thing, but depending upon the context in which you are using, their names keep on changing. So if somebody says you have an error amplifier, you inherently know that there is a negative feedback loop, and the amplifier that is embedded in the negative feedback loop is being referred to as the error amplifier. Okay. Okay, fine. We'll stop here. Thank you.